And it's my pleasure to introduce Slobodan from Universidad Federal Fluminense. I'm sure I butchered that. And he will tell us about retracts of free groups.
Okay, thank you very much for the invitation. What is a retract? A subgroup R of a group G is said to be a retract of G if there exists a homomorphism from G onto R that fixes all elements of R. Any such homomorphism is called a retraction. The retracts of G are exactly the subgroups that have a normal complement. I wrote a sketch of a proof. It's easy. Suppose that R is a retract of G and let rho be a retraction. Then clearly the kernel of rho intersects R trivially because rho fixes all elements of R. Moreover, it is easy to see that G is equal to the product of the kernel of rho and R. So the kernel is a normal complement of R. For the other direction, suppose that R has a normal complement in G, then G, suppose that the normal complement is N, then G is a semidirect product of N and R, and the projection of G onto R is a retraction. I will denote by Fn the free group of finite rank N. All free factors of Fn are retracts. However, free groups have many other retracts that are not free factors. In fact, free groups have a lot of cyclic retracts that are not free factors. And soon I will show you a complete description of cyclic retracts of free groups. I wrote here a few basic properties of retracts of free groups. Let R be a retract of Fn. The following assertions hold. First, the rank of R is smaller or equal than N. And equality holds if and only if R is equal to the whole group, if R is equal to Fn. Well, R is a homomorphic image of Fn. So R can be generated by N elements. Therefore, R has rank smaller or equal than N. Now, if R has actually rank equal to N, then any retraction from Fn onto R is an isomorphism. Now, if R is a proper retract of Fn, then the kernel of any retraction from Fn onto R will be a normal complement of R, and therefore it will be non-trivial. So if the rank of R is equal to N, then R is equal to Fn. I wrote one more property. All retracts or free groups are isolated. This means that if some non-trivial power of an element X belongs to R, then X belongs to R. This is really a consequence of the fact that free groups have the unique extraction of roots property. But I'm showing you this because soon I will show you that generalization of this property. Okay, a concept related to that of a retract is that of a test element. An element G of a group G is called a test element, or a test element for automorphisms, if every endomorphism of G that fixes the element, that fixes G, is an automorphism. Here are some examples of test elements of free groups. Let x1, x2, etc., xn be a basis for Fn. Then the commutator of x1 and x2 of the basis elements is a test element of F2. This follows from a theorem of Nielsen. Generalize this. In fact, C-Sham generalize this. The product of the commutators x1 and x2, x3, x4, etc., x2m minus 1, x2m is a test element of the free group of rank 2m. And the last example, x1 to the k1 times x2 to the k2, etc., times xn to the kn is a test element of Fn if and only if all of the exponents are different than 0 and their GCD is different than 1. This is a result of term. Here is the connection between retracts and test elements. An element W of Fn is a test element if and only if it does not belong to a proper retract of Fn. We'll give you an idea of the proof. So let phi be an endomorphism of Fn. Okay. Then the intersection of the images of all powers of phi, I should not use n here. This intersection is called the stable image of phi and is always a retract. Now notice that the subgroup of fixed points of phi is contained in the stable image. Okay. Now, if phi is not an automorphism, then it's not surjective because phi groups are Hopfian. Okay. So if phi is not an automorphism, then all points fixed by phi are contained in this proper retract, the stable image of phi. And the other direction is trivial. If an element belongs to a retract, then of course it cannot be a test element because you can think of a retraction. If it's contained in a proper retract, then it cannot be a test element because we can think of a retraction as an endomorphism. An endomorphism that is not an automorphism. Okay. Now, I want to show you a description of the cyclic retracts of free groups. For that, I need the notion of a visible element. Again, let x1, x2, xn be a basis for Fn. For every I between 1 and n, we define sigma xi from Fn to z to be the homomorphism which takes a word W to the sum of the exponents of all occurrences of xi in W. Show you an example. I don't know if this is clear. So consider the word x1 squared, x2 inverse, x1 cubed, x2, then sigma x1 of W. Well, x1 appears twice here, and the exponents are 2 and 3. So it will be 2 plus 3. It's 5. And sigma x2 of W. Well, we have 2 occurrences of x2, and the exponents are -1 and 1. Okay. Now, an element W of Fn is called a visible element if the GCD of sigma x1 W, sigma x2 W, etc., sigma xn W is equal to 1. It's not difficult to see that this definition does not, the notion of a visible element does not depend on the choice of a basis. I will show you a better way of thinking about visible elements. I don't know why I cannot show you the top, but it says, think of the point, think of P. P represents the point sigma x1 W, sigma x2 W, etc. Think of it as a point in Z to the n. then W is a visible element of Fn if and only if P could be seen from the origin. So here I have a picture. If n is equal to 2, then W is a visible element if and only if it's one of the yellow points here. The red point is the origin. And notice that the yellow points are exactly the points that you can see from the origin. And you cannot see the black points because the view is obstructed by some yellow point or some black point. Okay. And so here is the description of cyclic retracts. Let W be a non-trivial element of Fn. The cyclic subgroup generated by W is a retract of Fn if and only if W is a visible element. It's not difficult to prove this. And as a consequence, we get a complete description of the test elements of the free group of rank 2. So suppose that W is not a proper power, then W is a test element of F2 if and only if it is not a visible element. If W is a proper power, then we can write W as U to the n for some U that is not a proper power. And then it's easy to see that W is a test element if and only if U is a test element. And for U, we have the criteria. Now for free groups of rank greater or equal than 3, we don't have a complete description of test elements. Everything is much more difficult. We don't have a nice description of retracts because already for n equal to 3, we have proper retracts of rank 2. And so that makes everything harder. But I want to show you a theorem that says that there are a lot of test elements, that free groups have a lot of test elements. But first, I need the notion of a CNet. So let G be a finitely generated group, and let X be a finitely generating set for G. I will denote the word metric on G with respect to X by dx. A subset S of G is called a CNet with respect to X if for every element G of G, the distance from G to S is smaller or equal than C. Or a different way of thinking about this is that if you take any element of the group G and you look at the closed ball with center G and radius C, you always manage to find an element of S inside of the ball. So here is the result that I wanted to show you. This is a theorem that we proved with Euler-Snopchak. The set of test elements of Fn is a 3n minus 2 net with respect to every finite generating set of Fn. The property of being a net does not depend on the choice of a generating set. However, the constant changes when you change the generating set. Here it doesn't in this theorem. So the set of test elements is a 3n minus 2 net with respect to every finite generating set of Fn. So you don't have to take a basis as a generating set. You can take whichever other set. I want to show you the idea of the proof. Let P be a prime number. The property topology on Fn is defined by taking as a base of open neighborhoods of the identity the family of all normal subgroups of finite index some power of P. A subset of Fn is open in the property topology if and only if it can be written as a union of cosets of subgroups in N. Now, of course, this turns Fn into a topology. With respect to the property topology, Fn is a topological group, and we can take the completion. Let Fn p hat be the completion of Fn with respect to the property topology. It's called the property completion of Fn. The property completion is also a group. It's a topological group, and it's nice, it's compact, and it's Hausdorff. Now, the key step is this observation. You see, Fn sits inside of its property completion. Fn is a dense subgroup of its property completion. And if W is an element of if W, an element of Fn, is a test element of the property completion, see, we can see W as an element of the property completion. If it's a test element of the property completion, then it is a test element of Fn. And so the proof is like this. You take an element W of Fn, you look at it as an element of the property completion, and for technical reasons that we won't be able to explain now, it's easier to find a test element of the property completion that is close to W. And you can even arrange this test element to be an element of Fn. And then you use this fact here. So any test element of the property completion is a test element of Fn. Okay. The next result I want to show you is a theorem of Birdman. It says that the intersection of any family of retracts of Fn is a retract of Fn. Now, this sounds simple, but the proof of this theorem is actually very hard. It's clear that it cannot be trivial because there's no natural way of defining a retraction onto the intersection of retracts. In the same paper in which Birdman proves this theorem, this paper from 1999, he raised this question. Let R be a retract of Fn. Is H intersection R a retract of H for every finitely generated subgroup H of Fn? So again, let R be a retract of Fn, the retract R, and then you take an arbitrary subgroup H of Fn. You want to know if it's always true that the intersection is a retract of H. This question, in fact, was the main motivation for trying to understand retracts of free groups, because a positive answer to this question immediately leads to some nice results. Unfortunately, now we know that the answer to this question is negative. However, we have a partial positive result. This is a theorem with Snopche and Zaleski. Let H be a subgroup of Fn of rank 2, and let R be a retract of Fn. Here, N is arbitrary and R is an arbitrary retract. The subgroup should be of rank 2. Then H intersection R is a retract of H. Okay. And here's one nice consequence, nice corollary of this result. It's a bit technical. Let Wx1, x2 be a test element of the free group with basis x1 and x2. I'm thinking of W as a word. Let R be a retract of Fn. Now Fn is a different free group and R is a retract of Fn. And let A and B be two elements of Fn such that when you replace x1 with A and x2 with B, you get an element in Fn. And so we want this element to be different than 1. If WAB belongs to R, then A and B belong to R. So to give you an example, well, W, we can take W x1, x2 to be the commutator of x1 and x2. right? The commutator is a test element. In fact, every element in the derived subgroup, the commutator subgroup, is a test element. Now we have two elements, A and B, an arbitrary free group, Fn, and they do not commute. And so the corollary says that if you take any retract R of Fn, if the commutator of A and B belongs to R, then both A and B belong to R. So this is just one example, but this works for every test element. Okay, so as I said, in general, the answer to Birdman's question is negative. And in fact, for every m greater or equal than 3 and every k between 1 and n minus 1, this is the range in which the rank, this is the range, the possible range of the rank of a proper retract. There exists a subgroup H of Fn of rank m and a retract R of Fn of rank k, such that H intersection R is not a retract of H. Okay. Well, here's the simplest example that we could find. Well, there's a more geometric construction behind this. I don't know if this is useful to see the example, but here is the group H. Here is the element W. W is a visible element, so it generates a cyclic retract of F2. However, the intersection of H and R is not it's not a retract of H. And want to mention one more interesting result for this, the retract avoidance. It would be nicer if it's lemma. Let H be a subgroup of Fn and let Ri be an arbitrary family of retracts of Fn. See, if these retracts cover H, then H is contained in one of them. Yeah, this theorem also has some nice consequences, but I should be finishing. So I want to mention also the latest results on retracts of free groups. First, a definition: a subgroup K of Fn is called inert if for every subgroup H of Fn, the rank of the intersection of H and K is smaller or equal than the rank of H. Okay. So for example, if K, for example, if H is a retract, sorry, if R is a retract and if K is a retract and R intersection H is a retract of H, then we have this property. However, we saw that this is not always true. Antolin and Hiking recently proved that retracts of free groups are inert. And well, this is a well-known consequence. Basically, these two statements, these two theorems are equivalent, and as a consequence of the fact that retracts of free groups are inert, they got that for every set of endomorphism S of Fn, the fixed subgroup of S is inert in Fn. This was known as the Dixon Ventura conjecture, or the inertia conjecture, and it's by far the best result on fixed points of families of endomorphism. Okay, thank you.
All right. Any questions for Slobodan?
How do you prove these things? I mean, I know, but I'm just curious what sort of method is, or methods are employed.
For which things? We use a lot of Pro-P techniques for finite, but we also use geometric techniques. So it's a mixture of both. That's for our reason.
Any other questions? So I guess I have one. So for the 2m minus 1 net statement, do you know if the bound is sharp?
I never thought about that. It should be sharp, but
It should be sharp.
actually, I was thinking about that when I was preparing the talk. I'm not sure, but I think it should be sharp.
Okay, so your intuition says it should be sharp.
Yeah, because of the how the proof goes.
Okay, thank you. Any other questions? All right, if no, let's thank the speaker again. And I will stop recording.